Okay, this is problem number 6, chapter 19. So we have the magnetic field there at certain locations directly downward. So let's draw R. And so at some point it's directly downward. And it has a magnitude, so we'll use B for that, is equal to 50 microtesla. So remember, micro is 50 microtesla would be 50 times 10 to the minus 6 Tesla. And this is a proton is moving horizontally towards the west in this field at a speed. So we have what's happening is, if you think about it, let's just draw it in 2 dimensions. So this is into the Earth. So we're going to have our magnetic field going in like this. So we're showing the tail of the arrow. And so we have north, east, south, west. Okay, so it's moving west. Horizontally just means it's moving at one elevation. And it's moving west, which means it's moving from right to left. And it has a speed. So the velocity of the proton is 6.20 times 10 to the 6 meters per second. And it asks what is the direction and the magnitude of the force. So you use the right-hand rule to figure out the direction. So you'll take your hand, you point in the direction of the arrow, and then you'll curl your hand. So you use your right hand, and you'll basically be looking at the back of your hand. And then you'll curl your fingers towards the magnetic field. If you had your face of your hand, then you wouldn't be able to curl your fingers, so you have to turn it upside down and bend it in, and so the force is going to be downward. So it'll be south. So the force is in that direction based on the right-hand rule. As far as the magnitude, the relationship is that the force acting on a particle is equal to the magnetic field times the velocity times the charge times the sine of theta. And in this case, the angle between the magnetic field, which is going in, and the velocity, which is moving from left to right, is going to be 90 degrees. So the sine of 90 degrees is 0. And everything else we just plug in. The one thing we need to know is what is the charge on a proton. So if you go to the back of the book, I think they have the charge. Electronic, where is it? Elementary charge, E. If you look down that quarter of the way down, it says E is equal to 1.60 times 10 to the minus 19th, and the units are coulombs, because that's the unit of charge. So Q in this case, which is just the general charge that we're talking about, is a specific charge of 1.6 times 10 to the minus 19th. B, we already know, it's 50 times 10 to the minus 6 Tesla. Velocity is 6.2 times 10 to the 6 meters per second. So we just plug in. It's a substitution problem. And speed that over, give a little more space. So I've included all the units here. But the units for Tesla are a derived unit, so they're not a... Tesla is actually defined from this equation. So it's equal to newtons per, you'd end up with, if you solve for B, you'd get force, which is newtons. Velocity would be in the denominator, the charge would be in the denominator. So it's newtons per meters per second per coulomb, or newton seconds per meter coulomb. So if you plug that in for Tesla, you get the units of force for the answer. It's probably going to be a small number because it's, it's a proton. Now, if it was an electron, hold on a minute. If it was an electron, the force would be in the opposite direction, so it would be pointing up instead of down. Okay, now we put the numbers in. 50 e to the negative 6 times 6.2 e to the 6 times 1.6 e to the minus 19. That always makes it very small. The force is 4.96 times 10 to the minus 19th newtons. So let me just check the answer here. 1.5 times 10 to the minus, wait a second, must be the wrong problem. Oh yeah, that's the wrong problem. It's like, what? So it's 4.96 times 10 to the minus 17th. 4.96 times 10 to the minus 17th. Okay, so I'm going to read what it says here. Their explanation. Basically just, well, it doesn't really, it just says, using the right-hand rule, fingers pointing westward in the direction of V, so they move downward towards the direction of V as you close your hand, palm points southward. This is the direction of force exerted on a proton. Positive charges towards the south, and if it was a negative charge, it would go towards the north. Problem number 8. And what we have is we have an electron which has a charge of negative 1.6 times 10 to the minus 19th coulombs. And it says it's accelerated through a voltage of 2400 volts. And remember, voltage is equal to potential energy per unit charge. So if we take an electron that's at rest and we accelerate it, we're going to have a change in energy. So what we'll have is we have conservation of energy, which says the change in potential energy plus the change in kinetic energy equals 0. So the potential energy is associated with the voltage and the charge, and the kinetic energy is associated with the mass. So the kinetic energy is going to be, the change in kinetic energy is 1/2 mv final squared minus v initial squared. But V initial is 0. And that's going to be equal to the change in potential energy, which turns out to be the voltage times the charge. So we can solve for the velocity of the electron after it's accelerated. It's going to be equal to the square root, because we have this squared. And what else will we have? We'll have 2 times voltage times Q divided by the mass. So if I solve for V final, I'll get 2VQ over M, take the square root. So we get the final velocity. So even though we don't know the distance it's traveling, we know that because voltage is potential energy, the charge would use conservation of energy rather than Newton's second law. We probably can't use Newton's second law because acceleration is probably not constant. Okay, so let's plug the numbers in. So we have 2 times the voltage times the charge divided by the mass. And the mass of an electron is in the back of the book. Electron mass, 9.11 times 10 to the minus 31 kilograms. Two times 2400 times 1.6 e to the minus 19th divided by 9.11 e to the minus 31. Raise that to the half power, and I get 2.90 times 10 to the 1.7 meters per second. So that's the velocity. Now, it asks for the maximum and minimum magnetic forces, and that all depends on the angle between them. So the maximum is going to be just equal to the magnetic field strength times the velocity times the charge, and you have it times the sine of theta. So the max that can be is when that equals 1, and the minimum is going to be 0. So the maximum is when sine of theta equals 90 degrees. Sine of 90 degrees equals 1, whereas if we have the magnetic field and the velocity in the same direction, then the angle is 0 on the side of 0, so that's our minimum. So our maximum, though, is the magnetic field strength, which is 1.70 Tesla, times the velocity, which is 2.9 times 10 to the 7th, times the charge, which is 1.6 times 10 to the minus 19th coulombs. So even though it's moving pretty fast, the force is still pretty small, just because the mass is so small. Oh, that's not true. It's just small because the charge is small. Okay, so what I've done is we got 1.7 Tesla times 2.9 times 10 to the 7th meters per second times 1.6 times 10 to the minus 19th. And the force, the maximum force, is going to be equal to 7.9 times 10 to the minus 12th newtons. Just going to check, make sure that's the right answer. Yes.
Recording started.
Okay, we're on problem 13, chapter 19, physics. So let's read the problem. It's from page 656. It says a current of 15 amps is directed along the positive x-axis and perpendicular to a magnetic field. A magnetic force per unit length of 12 newtons per meter acts on the conductor in the negative y direction. Calculate the magnitude and direction of the magnetic field in the region through which the current passes. So, let's draw ourselves a conductor like this. So that's our wire. And there's a current along the wire in the positive x-axis. So we have, we'll call this x, we'll call this y, and we will have a z direction, which will actually be in or out of the screen. So anyway, the current is going in this direction. And so we have positive charges going from left to right, negative charges going from right to left. Okay, so the current is 15 amps. And so we either have a magnetic field going into the screen or away from the screen. We don't know yet based on, well, we can actually figure out the direction because it says the magnetic force per unit length. So let's draw a arrow in here just to show a force. And it says that it is in the negative y direction. So we're having a force going in this direction. So as far as which direction the magnetic field, well, it's always going to be perpendicular to the current and the force, so that's why it's either in or out. To be perpendicular to both these vectors, it has to be either in or out of the screen. Now, let's just try it. You have to use the right-hand rule. And so you point your hand along the direction of the current. And what we're going to do is we're going to you take your finger and you curve in the direction of the magnetic field. So if you're putting your hand and you're following the positive x direction and you curl your fingers in towards the screen, then your thumb should go up. So if we had the magnetic field going into the screen, then we would have a positive force. But because it's going downward is going to be the opposite. So you can do the same thing. If you took your hand and you almost have to turn it upside down, you point that, and then you curl your fingers away out of the screen, and you'll see that your thumb goes down. So we know it comes out of the screen. If it comes out of the screen, we use little dots to represent that. If it was going into the screen, we use little X's. So direction of the magnetic field is out of the screen. Okay, so once we know that, then we can just use the equation for the force, magnetic force on a current in a conductor. And so I'm looking back here in the correct section of the book. And so what it is, the force is equal to B, the magnetic field, times the current, times the length, times the sine of the angle theta. In this case, the angle between the current and the magnetic field is 90 degrees. So it's going from here straight out of the screen. So that the sine of 90 degrees is 1, and so we just end up with this, and we're going to say theta equals 90 degrees in this case. So the sine of theta, the sine of 90 degrees, is 1, and so the equation is just the force is equal to B times I times L. Okay, so let's have to go back and look at the problem again because I don't remember what it said as far as if there was anything about length given in the problem. Okay, so what they did, they give you a force per unit length. So what they say is the force per unit length is equal to 0.12 newtons per meter. So if we go take this equation, F is equal to force is equal to the magnetic field times the current times the length. We divide by the length, we get force per unit length. So we now know that part. And that's equal to B times I. And so now we can solve for B. And so we divide both sides by I. And so we get force per unit length. And we divide that by the current. And we know the current, and we know the force per unit length, so we have just put the numbers in. Our force per unit length is 0.12 newtons per meter. And our current is 15 amps. Since we have just newtons, we don't have kilonewtons or anything. We don't have kilometers, so meters, we have amps. The units are going to work out. And the units are Tesla, which have units of Newton meter amps, which is good because that's what we have, 0.12 divided by 15 amps. So we get 0.008 Tesla, which are the units for magnetic field for the SI system.
Recording started.
So we just took a little break there so I could check to make sure that was the correct answer. Which it is. I think they showed it as 8.0 times 10 to the minus 3 T Tesla. But otherwise, we're in good shape. Okay, this is chapter 19, problem number 16. And we have a wire that is moving from, let's see, where's the problem? Horizontally to the south, so this is north. This is south. What we're going to do is we're going to find east is going into and west is going out of the board. And then the force that they're looking for is a force upward. So as far as the direction of that force, you have the current moving here. So you put your hands in the direction of the current. You curl your hands towards the, maybe in here. Okay, to get the force to go upward, you have to curl your hands towards the east into the board. So to get an upward force, we have to go eastward. If we want to go downward force, because what's happening is we are balancing the weight. So we're given some information. We're given the mass per unit length is 0.5 grams per centimeter. So let's convert that to kilograms per meter. So you're going to divide by 1,000 to get kilograms, and you multiply by 100 to get the length units correct. So you end up with 0.05 kilograms per meter. And what we're looking for is the weight per unit length, because we're going to balance that with the force. So we need weight, which is force, which is a weight. So to do that, all we have to do is take mass per unit length and multiply by g. Mass is equal to weight is equal to n times g, which is 9.8 meters per second squared. So I get 0.49 newtons per meter. So that's weight per unit length. Now, if we look at the force on a current carrying wire, it is equal to, the force is equal to, summary here, it's equal to the magnetic field strength times I times L times the sine of theta. In this case, theta is equal to 90 degrees because the current is going north to south. The magnetic field is going into the board, which is east. So 90 degrees. So that means we just simplified down to this. And what we're looking for is we're looking for equilibrium, so that the force provided by the magnetic field is the same as the weight. So the force through the magnetic field is pulling up and the weight is pulling down. So if we look at the force per unit length we just need to set that equal to the weight per unit length, which is 0.49 newtons per meter. So we can and this actually, so this we divide that by L. So the first force per unit length, due to the interaction of the current and the magnetic field, is just B times I. So 0.49 is equal to B times I, or I, actually we're solving for B. So B is equal to 0.49, the units are newtons per meter, divided by I, the current, which is 2.00 amps. So 0.49 divided by 2 is 0.245 newtons Tesla. Units for magnetic field of Tesla. So the answer is 0.245 Tesla into the board will give you an upward force equal to the weight of the wire.
Started.
Okay, problem 17 is another current carrying conductor problem. And let's just read it and see how it corresponds with the diagram that you can see on the screen. So it says a wire carries a current of 10 amps in a direction that makes an angle of 30 degrees with the direction of a magnetic field of strength 0.3 Tesla. Find the magnetic force on a 5-meter length of wire. So you can see that the wire comes in and it creates a 30-degree angle with the magnetic field. And that just makes me think about this. I may have drawn it wrong. Actually, that's the wrong direction. So this thing has to be rotated around. The reason I say that is because if it was 90 degrees, then this thing would be perpendicular to that. So that's why that's incorrect. So since this is going to be 30 degrees, now if the wire and the magnetic field were in the same direction, you would get no force. If you have these perpendicular to each other, which would be an angle of 90 degrees, then you would have the maximum force. And the expression we just saw was force is equal to magnetic field times current times length times the sine of the angle theta. So I actually find the force in this case just a matter of plugging in the numbers. 0.300 Tesla, current of 10 amps, a length of 5 meters, and an angle of 30 degrees. So if we plug those numbers in, we get 0.3 times 10 times 5 times the sine of 30 degrees, which is a half, and we get 7.5. And because it's force, 7.5, and put a 0 because I have 3 significant figures. This would be 5.00 meters, I think. So we have 3 significant figures, so when you multiply things together, you always take the significant figure with the least number of the element that has the least number of significant figures and will drive the significant figures of the answer. So we get 7.5 newtons. Now, in terms of our drawing, it doesn't really tell us which direction this is going. So assuming the direction that we're doing here, if you take your hand and you take your fingers and point in the direction of the current, you'll be going at that angle. And then we curve towards the magnetic field. Well, if we take it and just curl our hands so that the thumb is pointing our face, you can see we're actually pointing opposite the direction the magnetic field is. So we really have to, again, take your hand and rotate it so your thumb is down, and then point your hand along the red line. And then when you curl it back towards your elbow, what's going to happen is that the thumb is going to go downward. And so in this case, you would end up having your thumb go into the screen. So in this case, the actual force would be pushing in towards the screen instead of away from the screen. So we'll say in towards the screen. They didn't ask us for the direction, but the more chances we have to practice that, the better we'll be at it.
Recording started.
Okay, problem 26, chapter 19. This is a current loop, and these are how electric motors basically work. And so we have a current I'm showing flowing from left, coming in this terminal, coming from the left-hand side. It goes around this loop, and then it comes out the right-hand side. And so you can see the loop has a certain circumference to it. And really, we're not so worried about the circumference. We're actually worried about the area that the thing makes. So given the circumference, we can find out what the radius is, and then we can back out the area from that. So we don't want to just use the circumference. And what happens is, here's the magnetic field going up and down the page. The current's going across the page. And so the torque is going to be force going, say, pushed in up here and pulled out down there, which will cause this thing to rotate in the plane. So it's like this would come out. Say this would go in and this would come out. Right now we're just seeing it at this particular orientation, which actually gives us the maximum torque. If this thing rotated 90 degrees towards me, then you would have zero torque. But anyway, so for a current loop like this, there's a simple equation that tells you what the torque is. So let's write out the equation. Torque, which is Newton meters, torque is force times distance, is the magnetic field times I times A, which is the area, times the sine of the angle theta. Well, in this case, the angle theta is 90 degrees. Okay, so the angle between the current and the magnetic field is 90 degrees. So you're going to get a maximum torque. So we can make this go to 1. So the torque is just equal to magnetic field times I times A. So we have everything except we don't have the area. So we're going to have to calculate that. So let's think about this. The circumference is equal to 2 pi times the radius. So the radius is equal to the circumference divided by 2 pi. And so if we take 2 meters and we divide by 2 pi, we'll get a number. 2 divided by 2 pi. And then to find the area of a circle is pi r squared. So we're just going to put pi times r, which is 2 divided by 2 pi, and we're going to just square that. And so let's just plug it into our calculator and get a number. So you'll have pi times the quantity 2 divided by 2 divided by pi, close the parentheses, squared, pi r squared, 2 pi r. So what I get is I get 0.318, and the units are, let's see, well, circumference was in meters, so the area will be meters squared. So all we have to do now is take the magnetic field strength, which was 0.800 Tesla, multiplied by the current, which was 17 milliamps, and then multiplied by the area, which is 0.318 meters squared. And so the torque, 0.88 times 17 times, okay, we've got to convert milliamps to amps, so we're going to multiply by, or we can divide by 1,000. Let's do that. Divide by 1,000. So 17 divided by 1,000, and then times 0.318. And so what I get is I get 0.0048, and it's going to be Newton meters because the torque is in Newton meter. And so the torque is 4.8 times 10 to the minus 3 Newton meters. And unless I wrote something down wrong, I'm not getting quite the right answer. So let me see if I can figure out what's going on here. Let me multiply and use my calculator again here. 0.8 times 17 times 0.318. No. Okay, that should be 0.43. That's the correct answer. So I just used my calculator wrong. And that's the answer in the book, 4.33, actually, if you round it up, 4.33 times 10 to the minus third Newton's meters. So the key thing to remember out of this, the equation is pretty simple. And typically in this book, we're going to have things happening at 90 degrees, so we don't usually worry too much about the angle unless it's specified. So, let's just go back to, if you go back into chapter 19, let's confirm that this angle is what angle I think it is. So it's torque on a current loop in electric motors. And so let's see what they describe the angle as. So what I'm looking for is if the field makes an angle theta with a line perpendicular to the plane of the loop, as shown in figure 19.15, the moment arm. Okay, so what they're looking for is the angle between a line perpendicular to the loop, which would be out or in or out of the screen, and the magnetic field. So if we have this going in and out of the screen, and this is a magnetic field, it's going to be perpendicular. So if I were to, I can have this Okay, make sure I'm doing that right. It says this result is valid only when the magnetic field is parallel to the plane of the loop. And the plane of the loop would be this flat thing. So if you were to rotate this around, so really that's, if you take a vector that's perpendicular to this loop, so it'd be going in and out of the plane, then that would be 90 degrees. If this thing starts to rotate around, then the perpendicular to the loop, so let me just see if I can draw this. So what we're looking at here is this cross-section of the loop, if you were to look in the side, and then you'd have the, now when this thing starts to rotate, you're going to start to see some part of it sticking up and part of it sticking down. Okay, so as this thing rotates in and out of the plane. And at that point, you've got the magnetic field, which is actually going in and out of the plane. It's in the plane of this. That doesn't change. And so if you were to look from the side, if you came in and looked at the side here, you would have the loop, and you would have this vector, which is perpendicular to the loop, and then you would have the plane. This would be the direction of the magnetic field. And so this is the angle we're talking about. So when this thing is flat and in the same direction, you get 90 degrees. But as this thing rotates around, the vector perpendicular to the loop and the magnetic field is going to go to 0. And when it goes to 0, there's going to be no torque because the sign of 0 is 0. So I'll try to explain it in class. It's a little hard to view things in 3 dimensions in a 2-dimensional situation.
Recording started.
Okay, we're on problem number 29, chapter 19. And we did a single loop problem. But to get the kind of torques that you need in a motor, you typically have to have quite a number of loops. So in this case, we have 200 loops, 200 turns. The dimensions are 3 centimeters by 5 centimeters, which we'll have to convert to meters. And you know, it doesn't say what the shape is, I don't think, but we're assuming that it's a square since they give us 2 dimensions. So it says, let's see, this is a coil. And a coil doesn't have to be round, it can be any shape. So in this case, it's square. And it says, find the magnitude of the torque. Part A says, find the current in the coil if the maximum torque exerted on it by the magnetic field is 0.15 Newton meters. So we have a 200-turn coil. The dimensions as such. This is the magnetic field, 0.9 Tesla. So the equation for a current loop, we just used that previously, but if we go back and we look at this equation 19.9a, it says the torque is equal to the magnetic field times the current times the area times the number of turns times sine of the angle theta. Okay, so that's the equation we need. And as you can see, the only thing we don't know is the current, I think. Find the current, yeah, okay. So the only thing we don't know, we know the magnetic field is 0.9 Tesla. The torque is 0.15 Newton meters. The current, we don't know. The area we can calculate by this equation for the rectangle. The number of turns is 200. And it says maximum. Well, the maximum is when this goes to 1, because the sign always goes from -1 to +1. So we know that for a maximum, we know, we could say that T max, the maximum torque, is when the sine of theta equals 1. And that's when theta equals 90 degrees. So let's add a page. So I think all we have to do is solve, well, let's calculate the area first before we do that. So we have 3 centimeters, which is 0.03 meters, times 5 centimeters, which is 0.5 meters. So we multiply those together, 0.03 times 0.05, and we get 0.0015 meters squared. So that's the area. Everything I think else is in the right units. Turns doesn't really have units. B is in Tesla, which is fine. I think that's it. So all we have to do is take this equation and solve for I, letting the sine of theta be equal to 1. So what we'll get is the current is equal to the torque divided by the magnetic field times the area times the number of turns. So all we have to do now is plug the numbers in. 0.9, so that's the magnetic field. The torque is 0.15 Newton meters. The magnetic field is 0.90 Tesla. The area is 0.0015 meters squared. The number of turns is 200. Because we have all the units in there, there's no prefixes or anything like that, we can just plug them in. So 0.15 divided by 0.9 divided by 0.0015 divided by 200. And, okay, so the number I'm getting is wrong because I got 2.5 times 10 to the minus 6, which is ridiculously low current, so obviously my calculator was wrong. I multiplied by 0.0015 instead of dividing it by it. So I get something here a little more reasonable this time. When I plug the right numbers in, I get 0.56 amperes. So that's pretty reasonable. We've been talking about fuses having 20 to 30 amps, so this is not an unreasonable value for the current. So that's part A. Part B says what will be the torque if the angle is 25 degrees. So all we have to do is take the torque and just multiply it by the sine of 25 degrees, so the maximum torque. So we have the maximum torque of 0.15 Newton meters, and we just multiply by the sine of theta. In this case, theta is 25 degrees. Make sure I got my mode right here. Degrees, I'm good. Sine of 25 degrees. Should be somewhat number less than 0.15. So I get 0.063 Newton meters. So let's just pause it. I'm going to check my answer.
Recording started.
So I've checked everything out and everything's good shape. So there you go. That's the answer. Okay, this is problem number 30, chapter 19. So we have a copper wire that's 8 meters long. It has a cross-sectional area of 1 times 10 to the minus 4 meters squared. The wire forms a one-turn loop in the shape of a square. So here it is. And this connects to a battery. So here's my battery. It's going to have a current flowing through there. And it's connected to the battery that applies a potential difference of 0.1 volts. This is 0.100 volts, 3 significant figures. If the loop is placed in a uniform magnetic field of 0.400 Tesla, what is the maximum torque that can act on it? So what is the equation for torque in a current carrying loop? So I look in the book, torque is equal to the magnetic field times the current times the area times the sine of theta. So again, when this is 1, the sine of theta is 1, we get the max, so the maximum torque is equal to B times I times A. And it says this is a, what does it say it is? Cross-sectional area, it's in a square. So we know that each side of the loop is going to be, so since the length is equal to 8 meters, then a quarter of the length is going to be the length of the side. I call that S. So each side is 2 meters long. Okay, what is the maximum torque to connect on it? The resistance of copper. So the resistivity of copper is 1.70 times 10 to the minus 8 ohms meters. So if you remember, resistance in a resistive element is equal to the resistivity times the length divided by the area. This area is the cross-sectional area, which is given in the problem. So this area, let's say this is A sub L, this is A sub C. A sub C stands for cross-sectional area. So here it is 1.0 times 10 to the minus 4 meters squared. And the length is going to be 8 meters, and the resistivity. So we can calculate what the resistance is. Why do we want to do that? Because I need the current. And I use Ohm's law, knowing that voltage and the resistance, I can calculate the current. Once I know the current, then I can calculate the maximum torque. So it's just a simple substitution problem with more than one step, more than one equation that we have to worry about. So there's our resistivity, our length, our cross-sectional area, and so the resistance of the wire .7 times 10 minus 8 times 8 divided by 1.0 e to the minus 4. So it's pretty low resistance. That's why the voltage was low. So it's 0.00136 ohms. And remember, Ohm's law says voltage is equal to current times resistance. Or we solve the current is equal to voltage divided by the resistance. The voltage is 0.100 volts divided by the resistance, which is 0.0136 ohms. So 0.1 divided by 0.00136, 73.5 amps, which is a pretty big amperage. And now all we have to do is just plug into the maximum torque. It's equal to the magnetic field times the current times the area. And that's the area of the loop. And the area of the loop, what is the area of the loop? Well, the area of the loop is the area of a square. And the square is made up of these dimensions, 2, 2, 2, 2, so they add them all to get 8 total. And so the area is just 2 meters times 2 meters. It's just the product of the two sides, which is 4 meters squared. So the current is 73.5 amps. The area is 4 meters squared. Therefore, the torque is the product of those three things. Which is 118 Newton meters. Torque is force times the distance. So let's just see if that's the correct answer. 118 Newton meters. What did I get? 118 Newton meters. Okay.
Recording started.
Okay, we're on problem 55, chapter 19. And let's just read the problem. It's on page 660, problem number 55. It says, two parallel wires are separated by 6 centimeters. each carrying 3 amps of current in the same direction. What is the magnitude of the force per unit length between the wires? Is the force attractive or repulsive? Well, we can actually answer the second question first, because if you go back and look in the book, you'll see page 645, it says active figure 19.28, and it talks about it, and it says the force is attractive if the currents have the same direction, so they're going to be attractive. And the second thing on that same page is a formula for force per unit length. And what they've done is they've basically said that what you do is you say one of the wires is creating a magnetic field, and then that magnetic field is acting on the second wire, and so that magnetic field acting on the second wire with a certain current is then, you can relate that to the force. That's how you derive the expression. So both of the current carrying wires create magnetic fields, and each magnetic field acts on the other conductor and causes them to have a force associated with it. Okay, so the expression is F1 is equal to mu 0, which is a constant, times I1 times I2, which are the two currents, divided by 2 pi times the distance between the wires. So in this case, distance is 6 centimeters, so we convert that to 0.06 meters. We know I1 and I2, and mu 0 is a constant that we would look in the book for, because we probably wouldn't remember it. And if you go to page 644, there's an example, and what the answer is 4 pi times 10 to the minus 7th, and the units are Tesla meters per amp. So now it's just a simple matter of substituting in the numbers that we know. So the force per unit length, and it'll be the same because the wires are carrying the same current. The forces are going to be the same. And actually, I was going to say that. Does that really make any difference? No, actually it doesn't. So they don't have to be the same. So the forces on the one wire and the other, they're equal to each other, because the only thing that changes is, maybe the order of these two, but the two currents are the same. So if this is 5 and this was 3, you would just have 5 times 3 as this part. The diameter distance would be the same, so it's irrespective. It's kind of like charges. It's kind of like Newton's third law, which says for each action there's an equal opposite reaction. So they would sort of have to be the same. I think I'm pretty sure about that. Okay, so mu 0 is 4 pi times 10 to the minus 7 Tesla meters per amp. And we multiply that by the current, which is 3 amps, times the second current, which is also 3 amps, divided by 2 pi times the distance between the wires, which is 0.06 meters. And I'm just thinking about units. I mean, what you would have to do is you'd have to convert Tesla to whatever the base units for Tesla are. We'll do that. But right now, since everything's in its kind of base units, amps, Tesla, meters, we can just do the calculation. And you can see that the pi's are going to cancel out for one thing. And you've got 4 here and 2 there, so that would become 2. So we'd have 2e to the minus 7 times 3 divided by 0.06 meters. So the first force per unit length is equal to 3.0 times 10 to the minus 5, and the units would be force per length, newtons per meter. So let me just double check that. So let's stop for just a second. I'll be back.
Recording started.
Okay, so that's the correct answer. You can see it's a pretty small force. And that's one reason why you have to, in an electric motor, you have to have a lot of coils, because the forces are small, and so the force is small, the torques are small. To get a reasonable torque, you have to have quite a number of windings. You also you could run a higher amperage, but 3 amps is pretty high. Okay, well, let's look at the units. If you go back to the definition of Tesla, so I'm going to Tesla, well, let's just look at it. We looked at the original expression for the force of a current of a charge. It was BI times L times the sine of theta. Well, this doesn't have any units. And so if you solve for B, you get force per amp per length. So the units of Tesla are newtons per amp meter. So if we plug that in there, let's go ahead and add another page and just do all the units. So for Tesla, we put in Newton per amp meter. And we multiply by meter per amp. Is that right? Yes, okay. So that's Tesla. This is the meters per amp part. And then we multiply by amps squared because we've got amp times amp, and we divide by meters from the basement here. So this cancels out with that. These cancel out with that. And so what you end up with is newtons divided by 1, divided by meter, divided by 1. And so when you do this, so I didn't just say get rid of this 1 because I've got this fraction, newtons per just the number 1, and then meters per 1. So when you do this, you have to take the reciprocal. So you've got newtons, and then you multiply by the reciprocal of this if you're dividing. So it's 1 over meters. And so the answer is newtons per meter, which is the correct answer. Okay, that's all. Okay. So we're going to do problem 57, chapter 19. It's the section of the magnetic force between parallel conductors. So let's just go ahead and write the equation down. So it says the force per unit length is equal to mu 0 I1 times I2. These are the two currents, divided by 2 pi d. So what happens with this situation is one wire creates a magnetic field, and the second one has the current flowing through that magnetic field, and the opposite happens the other direction. The other wire also creates a magnetic field, and that wire, the other wire, is going through the magnetic field. So we have a wire with the weight per unit length. Let's see, that's W1 per length, equal to 0.08 newtons per meter, just suspended directly above. So here's one wire, and here's the other wire. So let's call this wire 1 and this wire 2. So you have a weight that's pushing down. So the top wire, so we'll say I1, carries a current of 30 amps. The bottom wire carries a current of 60 amps. Find the distance of separation between the wires so the top wire would be held in place by the magnetic repulsion. So we want to have this equilibrium situation. So we got a weight per unit length going this way, and we have the force per unit length going that way. So the force per unit length comes from here. The weight is there. So we really could just set 0.080 newtons per meter equal to mu 0 times I1 times I2 divided by 2 pi times d. So it looks like we know everything. And that doesn't say which way they have to go. It doesn't say, but I think if they're going the same direction, they're repulsed. If they go opposite directions, they're attracted. So whatever the appropriate direction is. So really all we have to do is solve for D. So we'll get D is equal to mu 0 I1 times I2 divided by 2 pi times this force. So now we just plug the numbers in. So mu 0 is called the permeability of free space. It has a value of 1.26 times 10 to the minus 6. And the units are Tesla meters per amp. And we multiply by I1, which is 30 amps, times I2, which is 60 amps, divided by 2 pi times the weight per unit length. So it's just a matter of plugging into the equation. .26 times 10 to the minus 6 times 30 times 60 divided by 2 divided by pi divided by 0.08. So the distance I get is 0.0045 meters, which would be 4.5 millimeters. And that was problem number 57. So let me just check the solution. Problem number 57, 4.5 millimeters. I don't know why that wasn't that hard, so I guess we'll complain about that.
Recording started.
Okay, we're on problem 59. We have a solenoid. Solenoids are for creating magnetic fields. If we take some wire and then we put them in a loop like this, you're going to get a magnetic field associated with the wire, and all those wires stacked on top of each other create a magnetic field that looks like this, almost looks like a bar magnet. And so for a solenoid that has sufficient length relative to its diameter, there's a simple expression for calculating the magnetic field. So if we go to page 652, which is the summary of the chapter, it says magnetic field at the center of a coil of n circular loops of radius r, each carrying current I, is given by. So the equation says that the current is equal to the number of turns times mu 0 times I divided by 2 times r, which is the radius. So in this case, that's one thing. That's for a coil, though, so we got to be careful. So we're not talking about a coil, we're talking about a solenoid. So that's the danger of just writing things down. You got to make sure that you understand the restrictions. So you got mu 0 times n times I. So this is for a solenoid. What's the difference between a solenoid and a coil? A coil is just one loop. Okay, so mu 0 is a constant, n is the number of turns, I is the current. And you say, well, actually, this is the number of turns per unit length. So the small n is big N divided by L. So now we do have everything. We have n, which is 30. We have the length, which would change the meters. It would give us small n. We're actually trying to solve for the current. We know what the magnetic field is, and we know what mu 0 is. So it looks like we know everything. So what we'll do is we'll solve for the current. So this is, you need a certain amount of current to generate a magnetic field, and it depends upon a constant mu 0 and the number of turns per unit length. And n is equal to big N over L, so that you can say this is going to be B times L divided by mu 0 times n. So we have n over L, which is small n. So I just have to make sure everything's correct. Here we have Tesla, and actually millitesla, which is 10 to the minus 3. So we have 2.0 times 10 to the minus 3, that's the milli part, Tesla. Multiplied by the length, which is 0.06 meters. We divide by mu 0, which I think was 4 pi times 10 to the minus 7th or something like that. Okay, yeah. So it's 4 pi times 10 to the minus 7th Tesla meters per amp. And we multiply by the number of turns, which is 30 turns, which turns really are not, they don't have units, it's just a number. Okay, so let's plug the numbers in and see what happens. 2.0 e to the minus 3 times 0.06 divided by 4 divided by pi divided by 1 e to the minus 7th divided by 30. And so what I find out is the current has to be 3.18 amps, which again is a number that looks reasonable for current through a solenoid. So let's see if that was all they asked for. So we have find the current. Okay, so that was it. Hold on just a second and make sure this is correct.
Recording started.
Okay, so I've checked it, and that is the correct answer. Okay, this is problem 61, chapter 19. So it's about a solenoid, and it says it is desired to construct a solenoid that will have a resistance of 5 ohms at 20 degrees C and produce a magnetic field of 4 times 10 to the minus 2 Tesla at its center when it carries a current of 4 amps. Okay, so let's write what we did. We'll have what we did. We have a resistance of 5 ohms. Produce a magnetic field. So B is 4.00 times 10 to the minus 2 Tesla. And the current is equal to 4 amps. Solenoid is being constructed from copper wire having a diameter of 1.050 millimeters. If the radius of the solenoid is 1 centimeter, determine the number of turns of wire needed. So there's an equation, of course, that tells us about the magnetic field inside of a solenoid. So we look in the book, and there's 2 equations. We have the magnetic field is the number of turns times mu0 times I divided by 2r. And we also have B is equal to mu0 n times L, where n is equal to the number of turns per unit length of the solenoid. Okay, so we have a radius, we have a current, we know mu0, we know the magnetic field, so you should be able to calculate the number of turns needed. And what else we try to find here? So that's the number of turns. Probably something like length of the solenoid, I think. Length of the solenoid. Okay, now one thing is, they're telling us it's copper. So if we go back here, think about this. For a resistor, the resistor is equal to the resistance times the length divided by the cross-sectional area. So you've got the resistivity is a property, so we know that. The length is the length of the wire, not the length of the solenoid. And A is the cross-sectional area, so we can calculate the area. Area for a circle is pi d squared over 4, or pi r squared. So I think what we're going to do is we're going to calculate that, the area, knowing the resistance and the resistivity can calculate the length of the wire. Now the length of the wire is related to how many turns you can get around a particular radius here. So I'm trying to determine whether we're overspecified in some ways, but let me think. So we also have the relationship that the length of the wire is equal to, since it's wrapped around a core, it's going to be equal to the circumference, 2 pi r, times the number of turns. So I think you would be able to back out. Yeah, let me just stop and think about this for a second. I'll make sure I know what I'm doing before I start talking. Okay, let's get rid of this equation. This is for current carrying loop. We're interested just in the solenoid, which is this one right here. So, and I replaced, that should have been I, not L, that I had earlier. Okay, so what we're going to do is we are going to use this result to find the number of loops based on the length of the solenoid. So the number of loops limits how much wire we can have. So we find the resistivity for copper. We go back to chapter, whatever the chapter was that dealt with resistors, the property of resistance. So it was either 17 or 18. There we go, 17. Go to page 577, look for copper. Resistivity is 1.7 times 10 to the minus 8. And the units are ohms, meters. Okay, I'm going to plug that into there, so we'll have resistance is equal to resistivity times length, but length is 2 pi r times n divided by the area, which I can determine. And this diameter here is really, let's use the radius, because that's, oh no, that's right, that's the diameter of the wire, so that's right. And I can plug that in as well. This R is the radius of the solenoid. So I'm trying to decide if we solve for area and then plug that in, what we're solving for is the number of loops. So if we solve for n, we get R times A divided by rho times 2 pi, the radius of the solenoid. So I think we have, well, let's calculate the area. The area is pi times d, which was a half a millimeter, I think. Half a millimeter. So that was the diameter squared by 4. It's going to be a small number. You know, usually when you have this, okay, 0.5 squared times pi divided by 4. Actually, this area is not as small as half a millimeter for a wire. It's not super small. And let me just check, make sure I wrote that down right from the problem statement. 0.5 millimeters diameter. Okay, so I get an area of 0.0199 meters squared. Okay, now, so the number of turns is the resistance, which is 5 ohms, times the amps, which is 4.0 amps, divided by rho, which is 1.7 times 10 to the 8 ohm meters. Or is it 10 to the minus 8? It must be 10 to the minus 8. And then you multiply it by 2 pi times the radius of the solenoid, which is 1 centimeter. So 1 centimeter is 0.01 meters. Okay, 5 times 4 divided by 1.7 e to the minus 9 minus 8. divided by 2 divided by pi divided by 0.01. That's a really big number. So that's way too big. So what is my problem? I forgot the area somewhere, didn't I? Oh, I put in current instead of area. That's the problem. I got something like 10 to the 10th, which I knew was way wrong. So area is 0.0199. So let me fix that. Point 0.0199. Still a really big number. I'm getting 9.3 times 10 to the 367, 10 to the 7th. That's a really big number. So obviously I'm doing something wrong here. So the area seems kind of big that I came up with. Oh yeah, I forgot to change that to meters. So this should be this here. So I'm leaving this in here because I'm just demonstrating how you figure out when you're making mistakes. And so sometimes you make mistakes. You forget to do some conversion, and it's not the end of the world. Okay, so a millimeter is 0.001, so that's 0.0005. Yeah, that makes more sense, because normally when we do these areas, they're much smaller than what I was getting. I should have realized that. So I have pi times 0.0005 squared divided by 4, and I get 1.96 times 10 to the minus 7th. That looks better. Okay, so 1.96 times 10 to the minus 7th meters squared. Okay, let's try to get 5 times 1.96 e to the negative 7th divided by 1.7 e to the minus 8 divided by 2 divided by pi divided by 0.01, and I get 900. That's much better. So I get 903 turns. That'll give me a resistance of 5 ohms. Okay, now I go back to this equation here. So B, the magnetic field is mu0. Let me write this down. The magnetic field is mu0 times N times I. And N is equal to, this is the number of turns per length, so N is equal to capital N over the length. So I know everything here. Let me plug in. So the magnetic field is mu0 N, but N, small n is capital N divided by L, and times I. So I want to solve for I, for L. So that's going to be L is equal to mu0 Ni over B. mu0, look in the back of the book, which is the permeability of free space, is 1.6 times 10 to the minus 6. 1.26 times 10 to the minus 6. The units are Tesla meters per amp. Times the number of turns, that doesn't have units, times the current, which is 4 amps, divided by the magnetic field strength, which is 4 times 10 to the minus 2, 4.00 times 10 to the minus 2 Tesla. So the length of the solenoid, and I'd expect it to be maybe 5 or 10 centimeters at the most, 1.26 e to the minus 6 times 903 times 4 divided by 4 e to the minus 2. And so the length is 0.114 meters or 11.4 centimeters. Okay, I looked at the answer. I made a math error right here. So that should be 917 turns. And so that if you come back down here and replace that with 917, then your answer is slightly different. So we take 917, okay, times 4 times 1.26 e to the 6 and divide by 4 e to the minus 2. Okay. So it's 10 to the minus 6. Okay, so it's 11.5. You get 0.0116 or 11.6 centimeters. Okay, that's it. Okay, this is problem 70, chapter 19. So we have a wire that's carrying current, 2 amps. The mass per unit length is 0.5 grams per meter, which we can convert to kilograms per meter. So we're going to divide by 1,000, which means we're going to add 3 zeros in there. Let's make sure that's correct. So let's look for my calculator. Well, I know that's correct, so I need my calculator anyway, but not because of that. Okay, we have a magnetic field. So this is a current-carrying conductor in the presence of a magnetic field. So we go to the book and we look at the formula, magnetic force in a current-carrying conductor, and it says the force is equal to the strength of the magnetic field times the current divided by, multiplied by the length times the sine of theta. Again, because the current is perpendicular to the magnetic field, the current's going from left to right, and the magnetic field is going into the screen, the sine of theta is equal to 1, because 90 degrees is, theta is equal to 90 degrees, and the sine of 90 is 1. So we just end up with F is equal to B times I times L. We worked a similar problem where what we did is we converted the mass per unit length into weight per unit length by multiplying by G. So that would give us the weight per unit length. So if we take our value of 0.0005 grams per meter, or kilograms per meter, fix that, kilograms per meter, and we multiply by the acceleration due to gravity, which is 9.8. So it's kilograms per meter times 9.8 meters per second squared. That's going to give us newtons per meter. So 0.0005 times 9.8 is 0.0049 newtons per meter. So we can rewrite this force as a force per unit length by dividing both sides by the length, and you just get it's the magnetic field times the current. And what we have is, these are not equal to each other. What we're going to have is a kind of like a free body diagram, and you're going to have the weight per unit length pushing down and the magnetic force per unit length pushing up. And Newton's second law says that the summation of the forces in the y direction in this case is going to be equal to the mass times the acceleration. And if we divide by the length, you'll have the sum of the forces in the y direction per unit length is equal to the mass per unit length times the acceleration. So I have the mass per unit length. So what we're going to do is calculate acceleration. Is what we're looking for. So A is the force per unit length, summation of the force per unit length divided by the mass per unit length. And the forces we have acting on this is we have the magnetic force acting up, so that's B times I, and we have the weight per unit length going down, which is 0.0049 newtons per meter. So we can just plug in to find the acceleration. So we have the magnetic field strength, which we wrote down as 4 times 10 to the minus 3 Tesla, times the current, which was 2 amps, I think. 2 amps. And in the negative y direction, we have 0.0049 newtons per meter. That's the weight. That's going down. It's going up. So we take 4.0 e to the minus 3 times 2 minus 0.0049. And so our acceleration is going to be equal to, actually, I forgot to divide. Yeah, I forgot one thing here, didn't I? I've got to divide by my mass per unit length. So my mass per unit length was 0.0005 kilograms per meter. Okay. So the numerator ends up being 0.0031, which is the force and force per unit length, which is upward, which is good. So this is newtons per meter divided by kilograms per meter. So I get acceleration 6.2 meters per second squared. So let's just check the answer here before we go into the last part. Okay, so this is problem number 70 something, wasn't it? I think it was problem 70. And I'm looking 6.2 meters per second. Okay, good. So that is the acceleration, and the acceleration is constant. And so we can just use, what we're looking for is, I think, the time. It says, how long does it take? So we need time. So we have the 4 equations that we learned in the first semester, which said that delta y is equal to V0 plus V over 2 times T. We had that V is equal to V0 plus A times T. And we had delta y is equal to anyway, I'm just thinking here. They didn't ask us for distance, so we don't need to worry about that. So it's V0t plus 1/2 AT squared, and V squared is equal to V0 squared plus 2A delta y. So it looks like this one would be the one that we would use. Well, what do we know? We know V0 equals 0 meters per second. We know the acceleration is positive 6.2 meters per second squared. And what else do we know? Delta y. Okay. So delta y is 50 centimeters, which is 0.5 meters. So we actually need to probably use this one, right? No. This one. Yeah, that's the one. So since V0 is 0, we just get delta y is equal to 1/2 AT squared. And we know the acceleration of delta y, so we'll solve for t squared first. So we get 2 delta y over A is equal to t squared, and therefore t is equal to the square root of 2 delta y over a. So we have 2 times delta y, which is 0.5 meters, divided by the acceleration, which is 6.2 meters per second squared. And so the time is 0.40 seconds. And we'll check the solution to see if that's correct. That is correct.